Welcome to the lecture 7, and today we will be practicing applications of the Cauchy residue theorem to various integrals, complex integrals. So, okay, let me first refresh the memory regarding the Cauchy residue theorem. So let's start and let's look what it is about. So suppose here we have a domain. So the domain, put it like this. This is the domain. This is U. Of the function. So this is my U function, complex function. Let's say like this, C. So we denote this function f of z. This domain may have some singular points excluded. So let me exclude these singular points. I have one singular point here, another singular point, another. There may be several of them. So those are, denote them, Z1, Z2, Z3, and blah, 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 Z, and minus 1, and the last one is Zn. And then, of course, we have here a contour. So we may assume that this contour is it's like this. So let's see like this, write it now. So it's the first part of the contour. I may have another part of the same contour here. So call it C. This is also C. So this is two parts. Not necessarily here. And of course, and the bounded area by these two contours, like this is one contour bounded by, so we can say simply that C is a boundary of this region G, so the domain G. So the domain G is such that, so let's say like this. So suppose C contained in the U, so that's the domain of the function, is a contour such that it is a boundary of the region of the domain G. So G is not necessarily contained in this domain G. That means simply write it down. The boundary of G is equal to C, and that means the orientation is positive orientation, defined by this particular by this particular domain, and yes, and the function f has finite number of singular points. In G, and as we say, and means the function is not, for example, defined, so those points are excluded from the domain of the analyticity. So this, put it like this: Z1, Z2, and this is Zn, and they are all contained in G. So remember, function, these points do not depend on to U. So they are not part of U, so they were excluded from the very beginning. So that's how it is. So now, what we want to achieve, we want to compute the integral. So like this, 10. We want to compute this integral. So the integral over C, and I take this function f of z dz, and the answer is, that's the statement in the Cauchy residue theorem, that this one is equal to pi I, and here we have the sum, and this is k is equal to 1 to n, and that's a residue of the function f of z at the point zk. So, of course, it is it is appropriate to give you kind of a refreshment regarding what is actually the residue. So let me see, recall. So, for an isolated singular point, z0 of f of z, we have a Lorentz series expansion. Centered, we usually say centered. And z0, so let me write it down. So that means your function can be written as, so you have dots, 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 plus, and okay, let's say like a minus 2. There are many, many other powers possible. Z minus z0, 2, plus, and now I change the color because that's our residue. This is a minus 1. I'm not hiding it, so that's exactly residue. And this is z minus z0. This is plus a0 plus a1 divided by z minus z0. A1 z minus z0 plus plus a2 z minus z0 squared, and possibly many others. So of course, this part of this Lorentz series expansion, as you remember, we call it PZ. This is called the principal part. And that one, which we call AZ, that's analytic part of this Lorentz series expansion. Analytic part. Very good. So once we have it, so we should also remember that that value here, that's the residue. This is the residue of f of z at z0. So let me write it down. This is residue of f of z at z0 is exactly this a minus 1. And we will be using it definitely many times. So example. Start with the example number 1. So compute the integral. And the integral is exactly integral. Contour C will be specified. Here I just put here f of z. And here I put here zn plus a dz. We have seen this type of the integral, so where a f of z is analytic. Say everywhere, entire, even entire function. And b, c is a contour, positively oriented, of course. Containing only one single root, such that, and put here like this. C, only one root z0 of the equation z0 z to the power n plus a is equal to 0 is contained in the region bounded by C. Closed. Simple. Point. Okay. Of course, assume A is different than 0 just to avoid some more trouble. So we have this integral. We have seen this integral where we're actually solving these integrals in our previous lectures before we went online, and we were using the Cauchy integral formula to do it, and we had kind of the idea how to do it. But here, let me show you something. Since you have here this root, and then this is something like you see, Zn, so I can write it down. So that integral C f of z is analytic, so there is no problem here. This is Zn plus a dz. So we notice that first thing, that z0 is a simple pole. Simple pole. So remember, there are exactly n roots, and these roots are all different, so each of them appears only once. Simple pole. This is a simple pole, so we have here by the Cauchy integral, by the Cauchy residue, so the Cauchy residue theorem, we are getting this is equal to 2 pi I, and this will be residue of this function f of z to the power n plus a at the point z0. So recall how actually such residues are computed in such a situation. So here we have here f of z. This is z to the n plus a. So call that one like a p of z is the f of z. So let's say, and this is like q of z is the numerator and denominator. And then, of course, we need to assume a couple of little things. Let's say, assume that f of z0 is different than 0, just to make sure we do not have a removable singularity. And in such a case, if you have this situation, then of course residue, so remember residue, put it here, residue of such an expression p of z, q of z for a simple pole was given by this z value of p at z0, so this will be q prime at z0. So in such a case, what do I get here? That let's continue this one, make it like a space, make a margin, and that one is equal, and continue here, arrow. So this one is equal to 2 pi up. And we are getting the value of this function at z0. And this is n times z0 to the power n minus 1. N minus 1. And that's the answer for. So that's how this type of the integrals are computed. So let me take another example, more similar to this one, so we can apply these ideas, and put it like this. Example number 2. And here we have compute. And here we have integral c, and this will be my function is z e to the power z divided by z6 minus 1. So I emphasize again these types of integrals we were able to let's say, compute by applying the Cauchy integral formula. However, as you now are going to see, in this case, the method that we will be putting on is much more efficient, much faster. So here, the C will be equal, okay, so by the definition, this is positively oriented circle, such that Z minus 2 is equal to 2. Let me make a picture. So picture goes like that. So here we have here. So put here that's the value 1. This one is value 2. And the contour is the circle center and going like this. So maybe. And positively oriented that direction. Of course, we have also the roots of this equation, so they lie on the what equation? So this equation, Z6 minus 1 is equal to 0. Z6 equals to 1 has 6 roots, and we know where they are located. They are located also on another circle. It's here, unit circle. And we have here, maybe, this is my first root, this is my another one, and then the 1, 2, 3, maybe it should be 60 degrees. So it's here, it's here, it's here, it's here. So that's my root Z0, which is 1, then we have Z1, and is root Z2, Z3, Z4, and Z5. So that's a contour C. You can see only 3 roots of these equations are here. Notice that these 3 roots you have here Z0, which is equal to 1. You have here Z1, which is equal to, okay, 1/2 plus I square root of 3 by 2. Then you have here Z5, which is equal to 1/2 minus I square root of 3 by 2. Those belongs to this region inside. And then you, of course, you have here Z2, which is equal minus Z5. And you have here also Z3, which is equal to minus 1. And you have Z4, which is equal minus Z1. So all the roots are identified. So now we can just simply write the answer. Let's write the answer. Therefore, and you just simply apply the by Cauchy residue theorem. We are getting here that this integral Z, sorry, it looks like 0, C, Z, E, Z, Z6 minus 1BZ is equal, and this is 2 pi I, and then let's write it down. This is a residue, and okay, this is my function. This is my function f of z. That's my function f of z. So put it like that. This is my function f of z. So here I'm having here 3 residues. So this is f of z at the point 1 plus a residue. So that's my z0, and this is residue f of z. I will write just simply z1 for simplicity, and residue f of z, z5. So continue, so let's write it down, 2 pi I, and by applying the formula that we derived in the previous question, that one, you remember? We computed this one. That's here. This is our formula. Maybe put it in red. This formula. That's the residue. Let's use it. And we can write it down. I put it in brackets. So residue. So what do I get here? Bracket, and this will be 1. So this is Z0 is equal to 1 times e to 1. And then I have here derivative. So this is 6 times 1 to the power 5. And this is plus, and then you take the Z1, that's Z1. And this is e to the power Z1. And this is 6 times Z1 to the power 5. Plus, and this one is Z5, e to the power Z5, and this one is 6 times Z5 to the power 5. It is convenient to just multiply it by one more Z1, so this will be Z1, and then becomes square. This will be Z5, and then this becomes square. But what is this? Z1 5 times Z1. Have to write 5 like a 5 times Z1 is Z1 6, but Z1 6 is equal to 1. You see, those are the solutions to this equation. So this is going to be 1. And similarly for the other, so you can simplify the formula. This is 2 pi I divided by 6, and here we have e, and here I have here plus. This is gone, so this is Z1 square, e Z1, and this is plus, and that one is Z5 square, and this is e Z5. 5. And that's the formula. So now let me look again at the picture, and I see these 2 points here. Maybe I change the color. I use kind of a blue just to show you. See this one and that one. So these are 2 conjugate numbers. 2 conjugate numbers. So let me write it down. Let me write it down. Notice that Z5 is exactly conjugate of Z1. So Z5 square, maybe like make it nicer. Z5 square e Z5 conjugate will be the same as Z1 square e to the Z1. But remember, if you have 2 conjugates, like a number A plus number A conjugate, you will be getting 2 real parts of A. So in this case, this will be equal. I can write it down that value here will be equal to 2 real parts of the Z1 square e Z1. 2 real parts. So let me continue. So 2 real parts. So what is going to be? So let me compute it. So notice a couple of other things. So first, also notice that Z1 square is equal to Z2. Yep. You see, this is Z1 and this one is Z2. This one is Z1 square. So by looking at the picture and doing these things, we can basically find out what is the real part. So let's write it down. 2 times the real part of Z1 square is Z1 will be equal. So remember, Z1 was, actually I don't need to remember it, it's already written here. See? Yeah. This is my Z1. This is my Z3. Z2, sorry. Z2, which is equal negative of that one. So let's write it down. So this will be 2. And then I have here Z1 squared is Z2, so this is minus 1/2 plus I square root of 3 by 2. And then this one is equal E, maybe it's out, E to the power Z1, so this is 1/2 plus I square root of 3 by 2. Let's do this some first quick cancellations and then try to simplify it. So this is equal minus 1 plus I square root of 3. Then I have here, maybe put it here in the front, E minus 1, sorry, E to the 1/2, so it comes from this particular factor. And then I have here minus 1 plus I square root of 3. And here we have cosine square root of 3 by 2 plus I sine square root of 3 by 2, which provides us with the following. So maybe should write it now equals a real part of that one. So we just compute the real part. So you see this expression, this is 2 real parts. So let me do it. Real part. Okay, I should write the real part of everything here. Okay, I'm sorry. You see, those are punishable mistakes, so that you should never use it. You should never do it. You just write it down because you don't want to multiply everything. You just want to find out what is the real part. So maybe let's do it again. Yeah, it doesn't deserve to be messy. You don't deserve to have a bad presentation. So sorry. You see, in certain ways, things should be clear. So let me do it again. Let me compute these things again. Okay, write it down. This is. I will put it with 2 Z1 square E Z1 is equal. This will be 2. And then we have here minus 1/2 plus I square root of 2, so 3 by 2, so this is my Z2, and then I put here like this, E to the 1/2 plus I square root of 3 by 2, so we do the first simplification, we cut it, and then that one we factor out, so this will be equal, and this one is equal to E1/2, and here we have minus 1 plus I square root of 3 by 2, and this one will be cosine square root of 3 by 2 plus I sine square root of 3 by 2, and continue. We are getting E1/2, and now let's multiply. So this is minus cosine square root of 3 by 2. That's this 2, and this 2 give me minus, and this will be this. There is nothing. I should use the eraser. This eraser. You see, I'm trying to erase it. Maybe like this. Maybe just use this pen. I'm erasing. Okay. Yeah. So that's good. Okay. And this will be minus square root of 3 sine square root of 3 by 2. Now, plus I, that's imaginary part, again 1/2. But we are not interested in imaginary parts. So this will be just simply square root of 3 cosine square root of 3 by 2. And this will be minus sine square root of 3 by 2. And that's the real part, that's imaginary. So we can write the answer that C, Z, E, Z, Z to the power 6 minus 1 dz is equal to pi I. And here we have E plus, and this is 2 residues, which is equal to 1/2 minus cosine minus square root of 3 sine square root of 3 by 2. You can simplify it a little just to make it more elegant, 2 pi I. And this is E minus E 1/2 cosine square root of 3 by 2 minus square root of 3 sine 3 over 2, and that's the answer. So this is the answer. So this is like example number 2. Let's continue our examples. So let's go to the example number 3. Example number 3 is also possible to do it by applying the Cauchy integral formula, actually generalized integral formula. But our goal is actually to do the same example. So example 3 with the residue theorem. Example 3. And this time I would say, let's say this is my integral C, and we have here Z plus 1, Z plus 1, Z plus, sorry, always somebody is calling, Z plus 1, and this one is cosine Z, and this is Z cubed dz. And what is C? Where C is just a unit circle. This will be the unit circle, so this is Z equals to 1. So it's clearly. And by the theorem, by Cauchy residue theorem, we have here this integral, call this one integral I. Integral I is equal to 2 pi I, and this will be residue, and again call this function, for simplicity, f of z. So we get that this is the residue of this function at 0. So also notice that z0 equals to 0, you see, no numerator has, at 0 is 1, but that one has the power 3. That means this is the 0 of denominator or of multiplicity 3, 0. So you see this number 3 here. So you can say, notice that the 0 is a pole of order 3. So in such a case, usually, and this is a moment I can just simply remind you this formula, we would apply this formula. So if you have here, if z0 is a pole, write it down, put it like a remark, so like this, pole of order m, then this residue would be computed using the formula f of z at z0 using this particular formula. So it would be 1 over, and this is n minus 1 factorial. Since here everything will cancel, there will be no problem with the 0 as a kind of the singularity of the expression that I obtain after differentiation. So this will be just simply, in this particular case, it will be m minus 1, and this will be d zm minus 1. So after multiplication, so usually we take here, maybe put it in red. Here we just write it down, f of z times. Okay, put it here. Maybe write it down correctly. This will be like f of z times z minus z0 to the n. M in our case is 3. So it will be just simply 1 over 2 d second, this will be dz2, and here we have here z plus 1 cosine z divided by z cubed. Of course, you compute the second derivative and evaluate at z0. That's the way to do it. But we will do it differently. We will do it differently. In our case, we'll try to introduce a new method, a kind of the cool method for the computations of residues. Namely, we will try to figure it out. We will try to figure out what is the coefficient a minus 1 of the Laurent expansion, of the function f of z at 0. So let's try to do it. How to do it? Just simply, let's say we start with that one. So my function is like this. This is z plus 1 divided by z cubed, and here we have here the the function cosine. So this is cosine of z, and let's redo it. So we are getting here, this is z cubed, and then I have here z plus 1, so that's already Taylor series of that function. And then you have a cosine, which is 1 plus z squared divided by 2 factorial plus z 4 divided by 4 factorial minus z squared divided by 2 factorial plus z 4 divided by 4 factorial minus blah blah blah. And then you see which power I need in order to get the coefficient of minus 1. So minus 1 stands exactly minus 1, and here we have z. So if I have here z cubed, I have to multiply it by the power z squared. So that means if I have here 1 over z squared, z cubed, I must to find out what are, so this a minus 1 will be standing by the z cubed in this product here. Then I say, okay, let me look at that one. Okay. Why it is not disappearing? Okay, so we need to find out the z cubed. Say, look here, this is z squared, so that means if I multiply it by 1, I'm getting z cubed. But 10, nothing else, nothing else. So now you look at this one and say, okay, a minus 1 is exactly this coefficient. That one multiplied by this one. So this is equal to minus 1/2. And we have that this is actually our residue of f of z at 0, and we can write the answer. So the answer is that this integral, let's write it down, this integral again, integral over c z minus plus 1, sorry, z plus 1 cosine z divided by z cubed dz is equal to pi I, and the residue is minus 1/2, so this is minus pi I. Very good, so that's the third example. Let's go to the fourth example. Let me emphasize that these three examples could be handled by the Cauchy integral formula. The example number 4 would already create problems. And it is easier to deal with this example just by applying Cauchy residue theorem. So the integral, and here we have ez, and then I have here z cubed, and then I have here 1 minus cosine z, and this one is dz. So we see that here, if you look carefully, we have many, so maybe specified what is c, again the unit circle, and you can see that we have here many singularities. Clearly, you can see that 1 minus cosine z is equal to 0 if and only if, let's put it like this, zk is equal, so that will be 2 pi k, where k is equal to 0 plus minus 1 plus minus 2, so many. But look, that of course includes 0, so you may ask yourself what kind of singularity this point is, but these points are, but we actually don't need them all, because we look at the picture, our picture indicates us where is our integral. So our integral is here. This is the unit circle. 0 is here. The next point, the next singular point is somewhere here, 2 pi. And the other one is here, minus 2 pi. So these singular points do not participate in the computations of that integral. The only singularity that counts is our z0 is equal to 0. This is the only one singular point. So we can write it down, put it again. I is our integral, and then we can say 10 by, I don't know. Then by Cauchy residue theorem, we are getting here that this integral is equal to pi I, and here I have here a residue of the f of z, which is our function at 0. So what is our function? Okay, let me indicate it again. This is my function. Again, by simply analyzing the Taylor series expansion of 1 minus cosine z, you can realize that z0 is a pole of order, 5, so it's pretty bad. So in order to apply our formula, so in this setting, in order to apply the formula, so this by using formula, and this will be like residue of our function f of z at 0 will be equal, so look, this is 5, m is equal now 5, so this is 1, and this will be 5 minus 1, which is 4 factorial. Then you have here the 4 so no, this would be too easy. Limit as z goes to 0, and then you have here the 4th derivative dz to the power 4, and then you have to your function f of z. So this will be my function f of z. So which one it is? Which one it is? Aha, that's this one. So at the top is ez. So put it like this: ez, and the bottom is z3, and this one is 1 minus cosine z. And now I have to multiply to z to the power 5, and then take the 4th derivative and compute the limit at z is equal to 0. And even if you do this simplification, this is going to be kind of a difficult problem. Not for evaluating the derivative, but for evaluating this particular limit. We will show you later that this particular limit, even in the case of the order 3, can be kind of a challenging. So let me just point out that recommendation. Try to avoid this formula, the formula star for pole of order greater equal than 3 or 2 even. I would not even use it for 3. It could be too complicated, let's say. Greater to 2 actually is better. How? So if you have to avoid it, so how you are going to find this residue? In order to find the residue, you just simply, in this case, you just simply try to figure it out. So let's write it down. My f of z, we will try to figure it out, is equal, so what do I have here? So first of all, I have here 1 over z cubed. Then I have here ez, and then I have here 1 minus cosine z. I look at this 1 minus cosine z, and I try to, let's say, I'm going to play with the Taylor series expansions. So if you take the 1 minus z, so what do I get here? 1 and 1 will cancel, and we already have seen this series here. Just show you where this series was applied. Oh, remember, that is equal to the cosine of z. So this is 1, this to cancel here. Start with the second power. So let me do it. So this will be z squared by 2 factorial, and then you have minus z4, and this will be 4 factorial, plus z6 6 factorial, minus, and so on. I look at this guy and say, pull it out, take it out, and put it here, to this one. So that means I'm taking this and that one out. So let me rewrite it down. So I take this one, so I'm getting here 2, this 2, maybe say this 2 goes here, and this power 2 goes together with that one. So this will be z5. Then I have here ez, and then I have something that looks, maybe I put it in black, this something that looks like 1, and then I put here minus. I pull out z square out. Remember, we pulled out 2, so this will be 2 divided by 4 factorial. Good, and then you have minus, and this is 2z squared divided by 6 factorial. Then you have plus 2 z4 divided by 8 factorial minus and many more. So I look at this expression and I say, I really like this geometric series. I want to look at this particular expression as a geometric series. That means this one is going to be my q. Remember, z is close to 0, so it can be as small as you want. So you can make it, this series, very, very small. So that means actually this kind of a, can be considered as a kind of a sum of geometric series. That means this will be 1 minus q will be equal 1 plus q squared and plus. And that's what I'm going to use it now. So first of all, copy z to the power 5. Now, I also have here e to z, so this is 1 z to the 1 factorial plus z squared to the power 2 factorial plus z 3 to the power 3 factorial plus z4 to the power 4 factorial plus z5 to the power 5 factorial plus, close it, and then you have multiply it, and now I'm applying this particular power series. So this is my q, so that becomes z squared, sorry, 1 plus, and now q is this one, q is that one, so what is going to be? This is going to be z squared 2 4 factorial minus 2 z squared factorial 6 factorial, z squared 6 factorial plus, and then you have here dot, and then you have plus, and this will be z4 2 divided by 4 factorial minus 2z squared 6 factorial plus square, and other. Notice that here powers are larger, all larger than 4, and here all larger than square. So now I see, where is my coefficient a minus 1? A minus 1. So here we have the power 5. So we need to check out all the expression, because this is z to the power 5. So you have to have the coefficients. So you have to have coefficients, put it like this, b times z to the power 4. So everything that stands by the power 4. So where is my power 4? So let's see. Let's start here. Oh, I have a power 4 standing here. Never forget your your 2 that were pulled out there. So this is here, where is the coefficient? So I put it like this. In this part, so you have the power will be like this. Let me write simply coefficient. So write it down. A minus 1 is equal. So this 2 times that coefficient, because if you multiply this power by 1, you are getting 4th power. So this 2 gives me z4. So this will be 2 divided by 4 factorial. And if you would multiply z4 by z squared, it will be 6. No, that's not. We need power 4. So what else do we have here? 2. There are even powers, so only even powers will produce 4. So this will be my second one. Z squared, I have to multiply by z squared, which is that one. Yeah, so that will give me the power 4. So I put here plus, and then I have again 2, because there's always 2. And then I have here 2 factorial that comes from here. And then you have this one standing here. So times 2 divided by 4 factorial. So that's done. Then I say, okay, so where is another 4? Another 4 is here. This is 4. Z squared and z squared is 4. What is this one? This one is 1. Yeah, that means I'm getting power 4. But here's minus. So again, I tell you, you have to multiply this by 2, this is 2, and then you have here 2 divided by 6 factorial. But there's another power for here, but that means this one has to be taken square, so put it like this again, 2, and this one is 2, 4 factorial square. 4 factorial square. And we are getting the answer. Our integral of c, and this was where's my integral? Oh yeah. Where's my integral? Oh yeah. So this is integral. Z is z cubed 1 minus cosine z dz is equal to 2 pi I, and then okay, let me pull out something. I pull out 2, and this is 2 factorial. Do kind of a simplification. 1, and this is plus, and that one is 1 if I pull. And that one is minus. This was pulled out. So this is 2 divided by 5 times 6. 5 times 6 is 30. So this is 115. And then you have here plus. And that one is 2. So this will be 2. So this will be 4. And 6 times 4 is 24. 24 divided 24. And yeah, 24. Okay, I'm able to simplify it. So this one is equal 4 pi I divided by 4 factorial. This one is 2, and this one is minus 15, 24. So this is minus 15, and this one is plus 1, 6. And then, okay, finite simplification. So this is pi I, and this one is 6, and this one is 6 times 39. 90. This is 90. 180, and this one is 90, and this one is minus 6 plus 15 equals pi I over 6 plus 9, so 189 divided by 6 times 90. So this one, I can simplify. This is pi I 6, this one is 63, and this one is 30, so that one is 21, 15. Okay, the answer is pi I 21 over 90. 21 over 90. Yeah, something like this. If I, of course, did it correctly, this would be like this. So answer, like this, answer, hopefully. So this one will be 21, 90 pi I. That's a nice form. Let's say that's a nice standard form. And I believe we have time for a few more. Let me do this one. So another example. So which one example? I've already lost the count of the examples. This was 4. So let's go to 5. Example 5. Example 5. And let's compute integral over c, and this is z. I don't know, I put here n, arbitrary number. And this will be sine 1 over z dz, where c is positively oriented unit circle. So what are the singularities here? You can see that the only singularity is here because this function cannot be evaluated for z 0 equals to 0. So this is your singular point, and you know very well that this particular singularity is essential. Actually, we will compute as there is no other way to find the residues for the essential singularity than just by analyzing the Lorentz series expansion. That's what we are going to do. So call this one I, write the answer that my integral is sorry, I don't need to write it. This is 2 pi I, and this will be my residue of the function. This is my function. Put it like usually we put it. This is my function. This is my function. Sorry, something happened. It will work now. F of z. So this will be residue, this function f of z at 0. So we need just that number. So let me do it. So zn. And function sign is well known, so this will be just simply 1 divided 1, so 1 factorial z. Minus, and this will be 1 divided by 3 factorial z cubed. Plus, and this will be 1, again, this will be 5 factorial z5. And that's exactly, because we remember sine of z is equal, and here we have k is equal 0 to infinity, and minus 1 to the power k, z to the 2k plus 1, 2k plus 1 factorial. So I just simply replace z by 1 over z, and that's what we are getting. Minus, and this will be 7 factorial z to the power 7 plus 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 plus. So interesting. What do we need? We need to compute a minus 1. So a minus 1 means if this power is zn, so here I need the power, let's write it down. What do I get here? I need the power z, and this has to be n plus 1. N plus 1. So you can immediately notice that if this is the n, so this power appears here only if n is even number. So you can start writing your answer. So answer is going to be like this, answer. So this integral will be equal 2 pi I, and maybe write it down like 2 cases, 2 pi I. So now we have here this a minus 1 is my residue. So this is my residue a minus 1. So I put here a minus 1, and this a minus 1, you see, if n is odd, then we don't have it. So this is equal times 0. So this is equal to 0 if n is odd. And this will be equal to 2 pi I. And then if n is even, so put it like this, n is equal to m. This is even, so then you are getting here that here it will appear here like this. This will be 2m plus 1 factorial, and this will be 2m plus 1, and then this power will be z to m, cancel, and we are getting, that's the residue. So it will be in this case 1 divided by 2m plus 1 factorial, and this will be not 0. So we solve this problem. And now we can maybe just just do one more problem. This was which one? Yes, 5. Example 6. Example 6. So let's compute another compute integral, and this will be e z, and this will be z sine of z dz, and here c is again the unit circle. So since you practice and you know how very well how to determine the kind of the singularity, you can easily notice that z0 equals 0 is a pole of order 1 here, 1 here, so this is order 2. This is a pole of order 2, and there are also other zk equals pi k, and those are single points. Single poles. Simple poles. So let me look at the picture. So the picture looks like that. So this is my unit circle. One of the poles, z0, is definitely here. And this is my number 1. And the next one, pi is here, minus pi is outside. So okay, they're only 1. So in such a case, you can rewrite it. Now c is z. This is equal z sine z dz is equal, by the Cauchy residue theorem, 2 pi I, and this will be residue of this function. Again, this is my function. This is my function f of z. So I just simply write it down, f of z at 0. So let's compute the residue. Let's compute the residue, but I'm afraid I will not have enough space here. But okay, let's start writing, and then we switch to the next paper. So what is this residue? And here f of 0 at 0 is equal. And so this is order 2. Order 2. So there is a 1 divided by 1 factorial. Then we have here limit z goes to 0. And then we have here derivative d dz, just one derivative. And this is z is z. Actually, I should write it down like that. I should write this is equal e z. This one is z times sine of z. And then remember, here we put here z. This is order 2, so you put here this into z2. And let me compute it. So this one is equal limit z goes to 0, and here we have here e z is z. Just call it like this, d dz, z is z divided by sine of z is equal, and limit. Let's do it. So this is equal to 0, and what do I get? E z, z plus 1 sine of z. You just check if the derivative that I am writing here, cosine z, is computed correctly. And then one simplification that is possible to do is you pull out ez, and that means this is e. You can write it down like this. This is limit z goes to 0. This will be ez. and 10 times limit, and this is z goes to 0, and then we have here sine square z, and this one is z plus 1 sine of z minus z cosine of z. Z cosine of z. Let me do it, and let me check it. So what was our, where we are? So this was like a limit. Z goes to 0 is z times limit, and this one is again z goes to 0, and then we have here z plus 1 sine of z minus z cosine of z sine square z. Yeah, that's complicated limit. You can remember one thing, that since the real analytic functions and, let's say, complex analytic functions, they coincide on the real numbers. So that means if you have such a limit, this limit will be the same, and we know it exists. This will be exactly the same as for real functions, so why don't we just use the L'Hopital's rule? And that's what we are allowed to do it. So this will be L'Hopital's rule. So first limit is 1, and then we have here limit, and this is z goes to 0, and then we have here, what do I get here? Let's say apply the L'Hopital's rule, so we are getting here sine of z plus z plus 1 cosine of z plus z sine z, and again minus cosine of z divided by 2 sine of z cosine of z. Then you see something simplifies. This simplifies. So it's good. And then I can rewrite it, limit, and z goes to 0. And what do I get here? I can rewrite it now. Look, I can take a sine of z, 1 plus z, that's this 2, z together, and then I have z cosine z, so times, so I put it like that, put it like this, this will be 2 sine of z times 1 over cosine of z plus another limit, z goes to 0, and this is 1 divided by 2 cosine z, and there was a sign, but it simplifies, so I write it down, and now I just compute it, and I'm getting here, this is 1, this one is cancel, so I'm getting here 1/2 plus 1/2 equals 1. Oh, I got it. So I can write the answer. So the answer, our integral is equal to 2 pi I, that's it. 2 pi I, residue is 1. But that's not all, because I want to show you that this residue can be also another way of computing without the limit. The same as we were trying to do already. So here we have here divided by z, and this will be sine of z. So I will do it like it was before. This one 1 over z. This will be 1 plus z 1 factorial plus z squared 2 factorial plus, and then I have here 1, and this will be z minus z cubed 3 factorial plus z 5 factorial minus. I pull out this z, so what do I get here? I'm getting here 1 over z squared 1 plus z 1 factorial plus z squared 2 factorial plus, And then I will be getting here, just do it quickly, minus z square, and put it like this, 1, 3 factorial, minus z square 5 factorial plus plus plus. So this will be my q, so I can rewrite it down here. This will be 1 plus z, maybe I should use black. 1 plus z square 1 3 factorial minus z square 3 factorial, sorry, 5 factorial plus 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 plus, and then you just look which are the powers. So I need the first, so you need the first power, because this is z squared, so we are looking for the first power. First power. And that's clear, that's the one. There are no other first powers. So in such a case, a minus 1 is equal to 1. And that's the same residue that we obtained in using the limits. So as you see there is a difference between the effort that you need to put into these computations. Here you could notice quite easily that the figuring out the Lorentz series term a minus 1 can be much simpler than computing the limits of complicated expressions. So thank you. This is the end for today.